So yeah, without further ado, let me tell you about one of my favorite weird metrics. It's called the Pentagon Pizza Index. And for those of you who haven't heard about it, the idea is simple. So when the crisis is brewing somewhere in the world, late-night pizza deliveries around the Pentagon suddenly spike because the staff can go home, so they order in. Makes sense. And some people even try to use it as a predictor of major geopolitical events. But I'm not here to talk about geopolitics, fortunately. I'd rather focus on the pizza. So imagine that you're just a regular person, super hungry, walking through the streets of DC. You stroll into one of the pizza joints and ask for a slice of pepperoni cheese. And the cashier says that, well, you're going to have to wait several hours because they're backed up with huge orders, probably from Pentagon. And so we're sorry, we can't serve you. And so you storm off, hungry, angry, and thinking to yourself that it's totally not fair. You just wanted a single slice. And then you vow to yourself to never go into that place ever again. And you know what? You'd be right, because it isn't fair, and they should have done better. So today, we're going to see how can we fix this. I'm Alex. I'm a backend engineer at Evil Martians, and being a consultancy, we've met with similar issues a number of times on different projects, ranging from tools for developers to tools for creatives, with the most recent case being my own experience. And so today, I want to share all of that knowledge with you, practical tips that you can apply in your projects to make background jobs fair for all users. OK, so let's get back to our example. But let's look at it from the perspective of the business owner. Now, imagine that night you were snoring peacefully in your office because you have a great business, it just works. And you don't worry. Why would you worry? Because, well, you have a simple system and it works. You have your chefs in your kitchen. You have a single queue where all the orders come in. And all of those chefs are processing the same queue. Simple. And then that night, you received a ton of orders from the same customer, probably, again, Pentagon. And that's good, more money for us. But then another customer came in, and we were unable to serve him. So for the business, it's super bad, because we just lost a consistent stream of revenue. And what went wrong? Like, everything is great. Our chefs are exceptional. They're as productive as they can be. And the answer to that, of course, is latency. So the time that the orders spent in the queue. And how can we decrease it? Well, we can just hire more chefs. But this is expensive. And also, it's not like we're always going to have enough work for them to do. So what if we hire like part-time chefs? So they would just come work for us in peak hours. And it's great, awesome solution, but how far can we scale it? Or how far can we auto-scale it? To be honest, not that far, because so first of all, we can't hire infinite amount of chefs to get rid of all of the latency, because we don't have an infinite amount of space in our kitchen to fit infinite chefs. Similarly, we don't have enough background connections, by the way. But even before that, it's going to become counterproductive, because just throwing more money at a problem would just lead to diminishing returns. So what else can we do? Let's see. Now imagine, what if instead of just serving this queue, we do this? Of course, that's not how queues work, but let's just imagine for a second. And as you see, the total time to process this queue is exactly the same. So the latency would be the same, but we don't lose a customer. And the best thing about it is just Pentagon didn't even notice it. So what can we learn from this? we can learn that when the latency is high, and for some types of jobs, we can just expect it. It's going to happen. That's just life. Fairness really matters, because the greater the latency, the greater the need to treat customers fairly. But what is fairness anyway? Can we measure it? Sure. So there's Jane's index. It's used in networks. There's also Gini index that is used to measure inequality in economics. Maybe some other guy also has an index. But we don't really need to know how to measure it to know whether we have it or not. And so if you have a first-in, first-out queue, you have high latency at least once in a while, and you have greedy users, and you haven't done anything about it, you probably have it. But, OK. Even before that, your customers would have probably tell you about this in uncertain terms. So, all right, we're not being fair. But how do we start being fair? And, well, fortunately, intuitively, we already know what to do. We just need to split our shared resources, in this case, it's a pizza, equally. And proportional to the appetites of our users, but never at the expense of others. So let's see. We give the first slice to the mouse. Mouse is small, so it's already full. So we give another slice to the cat. And then another one to the pig. Then, since the mouse is full, we give the next slice to the cat again, and now the cat is full. And so we give the rest to the pig. Now, the pig would probably like to eat the whole pizza, but it's going to do. Like, it's fine. So everybody's happy overall. And this is fairness, in my opinion. So what do you guys think? This is fair? OK, good. So how can we implement this in, on queues? Simple. We just have a queue per customer. And then we pull at them at random. Now, this approximates our model super well, because everybody is treated equally. So, problem solved? Unfortunately not. Because since we have a queue per customer, we're going to have a lot of queues. And worst of all, we're going to have dynamic number of queues. And our background processors are just not built to handle that. So let's look at Sidekick, for example. In case of Sidekick, the free version is going to make this request. Like every worker, every chef, is going to make this request to Redis when it wants to pull a job into work. It's actually pretty good. It's just a single request, no matter how many queues you have. And it's blocking, meaning that it's going to wait. If all of those queues are empty, it's going to wait until there is a job for them to do. So it's not going to poll Redis and put a huge strain on it. But Sidekick doesn't support dynamic queues. So even if all of those queues are empty, it's going to like send them every time. So overall, not that bad, but not ideal. Let's look at Sidekick Pro. Sidekick Pro is going to make, so it's more reliable, which is good. But for our intents and purposes, it's even worse. Because due to some limitations of Redis, every worker is going to make these requests. One query per queue, per tenant. And those requests are not blocking. So if they return nothing, the worker would have to make this query yet again from every worker. So it's going to put a lot of strain on your Redis. What about Solid Queue? Solid Queue uses relational databases underneath. So this is the request that the workers are making. But again, it's not much different. So it has to make a single query per tenant. And also, it polls. So you're going to put strain on your relational database. Then we have Good Job. Now, Good Job, well, it uses advisory logs, so different mechanism for locking, for kind of managing concurrency. But it also uses, well, it relies on Postgres channels as a best effort pops up. So it's not going to poll as much, but again, it's a query per tenant. So what's going on? Like, is it really that difficult to implement it? to have a background processor that actually handles multi-tenancy? And not really. Well, it adds an overhead, but overall, we can do this. But you need to realize that all of those processors are built with simplicity and performance in mind. They're general purpose. And so, and our problem, to be honest, well, it's kind of niche. Like, not every job needs this fairness and support for multi-tenancy. So what are we left with? Do we just build our own? No, of course no, because the background processors are not just pushing stuff into queue and pulling stuff from the queue. They're also retries, safety, crash safety, and so on and so on. So instead, let's see what can we do with what we have. And so today we're going to look at the 4 strategies: shuffle sharding, interruptible iteration, throttling, and per tenant queues. Keep an eye for the last one, because it's going to be pretty different. So let's start with shuffle shards. Now imagine, instead of a single queue, we have 3 queues. Not many queues, just 3 queues. And to each of those, we assign their own chef. We can assign more chefs, but for this example, just 1 chef per queue. And we also determine a way how we route customers between those queues. This has to be deterministic and preferably random, but for our example, again, let's stick with just deterministic. And this is what we're going to do. The customers whose name start with letters from A to I go to the first queue, from J to R to the second, from S to Z to the third. And let's see what's going to happen. So far so good. We process the jobs, but then we immediately see a problem. The second chef ran out of work, and instead of helping the first one to process the Emmy's order, he just sleeps. Not great. However, when a big customer comes in, it doesn't block neither Emmy nor Sam. So, awesome. But unfortunately, it will block Joe. Sorry for all of the Joes in the audience. So, what can we see? What can we say about this approach? As we saw, blocking can still absolutely happen. It's just less likely. How likely depends on how many those shards, those queues we create. And also not perfectly fair for Joe, for example. But when it isn't fair, it affects less people. And it also has a problem with underutilization. So not ideal, but this approach sure does scale. And like, it's super cheap to implement. Well, it's basically free. So it's super powerful. So let's look at the next one, the interruptible iteration. So imagine we have in our queue 3 orders for a slice of pizza from the same customer. But in our example, I think it would make much more sense for a customer to create 1 order for 3 slices instead of 3 separate orders. So let's treat it as such. And what have we achieved? So far, not much, because a single order can be processed only by a single worker, which just made the processing 3 times slower. But it's easy to fix. If we have enough work in our queue, all of the chefs will be utilized. But the advantage of this approach lies in its name, interruptible. So the chefs, instead of processing the whole order, they can just process a slice, a single slice, and kind of put a bookmark on the order and just throw it back to the end of the queue. And what's good about it is that it doesn't block, as you can see, the customers behind. However, if the same customer decides to create many batches for many slices, then the fairness kind of goes out of the window. So again, unfortunately, the blocking can still happen if the same customer is allowed to create many batches at the same time. And that's when it stops being fair. But we can say that at least it doesn't have an underutilization problem. And it also scales very well because it just needs to store some cursors in Redis, probably. And it's super cheap. So if your work comes in large batches, naturally, this is a good approach. Let's look at the next one. The next one is called throttling. So imagine that we have a single queue, and we notice that a single customer is being greedy. But you ask, like, how do we tell that someone is being greedy? And you can choose a number of approaches, but my favorite is the leaky bucket algorithm. It unsurprisingly emulates a leaky bucket, and it's super efficient, space efficient, and also CPU efficient. And it has a very nice property. When it overflows, it tells us about this. And we can decide what can we do with this like excess water. In our case, it's orders. So we can decide to put those excess orders, kind of spill them onto the second queue. And then, what if we do this? What if we just assign different chances to those queues? So we're going to pull at them at random, but not exactly at random. So the first queue, we're going to pull from it with 80% chance. So it's going to be the fast, the default queue. And the second queue is going to be the throttled, the slow queue, from which we're going to pull with 20% chance. And what's good about this approach is that when that customer creates a ton of orders, again, all of those orders are put into the slow queue. And so it doesn't block the customers behind. Good, nice. So, like, what's the catch? The catch is if at some point we decide to stop punishing that customer, all of the orders that were already put into the slow queue are kind of stuck there until they finally get processed. However, there's also a small advantage. If the default queue is empty, we can start processing the slow queue at the full speed. So this approach is really nice. So the full blocking never happens because everybody will have a chance to process at least something before we start punishing them. And it also scales extremely well, especially with leaky buckets. And it doesn't have a resource utilization problem. The catch, of course, is if your workload is bursty by nature, you're going to have a problem with fairness. And by bursty, I mean like when your users create 100% of their requests in 10% of the time, instead of kind of microdosing and creating 10% of requests 100% of the time. So, OK, but overall, not a bad approach. So let's look at the last one. And now let's take a step back and think what the previous three approaches have in common. And, well, first of all, they scale very well. They're super cheap. And they all have edge cases. So if we want something universal, we need something radical. We need to hire a manager. And not just a manager. We need to hire a manager with a huge ledger where all of the orders will go in instead of going to the main queue. And, well, actually, the guy is just sleeping most of the time while the chefs are doing the job. But once in a while, he wakes up and he sees that they're running out of work. So he throws some more work at them into the main queue. And then he sleeps again. OK, so what have we achieved? So far, again, not much. So for the chefs, nothing has changed. They might not even realize they have a manager now. And to be honest, we just introduced a bottleneck. But if you think about it, we also introduced an arbiter, a single point of making decisions. And it could be like super smart. What if like a wizard of fairness, and it knows how to do one thing and do it well. And the way he does it is totally up to him. But we can imagine that he would do the same thing that we discussed at the start of this talk. So, what can we say about this approach? It's basically communism, if it worked, meaning that it's perfectly fair and it's super efficient because, well, underlying infrastructure didn't change. So it's kind of perfect, but there's a small caveat. It is a bottleneck. However, not all bottlenecks are created equal, because if it's able to push a new batch of jobs to the main queue faster than those jobs are processed, then it's not really a bottleneck. And for heavy jobs, especially for heavy jobs, it's an extremely good solution. And what jobs I'm talking about? Like AI workflows, for example, because suddenly everybody wants to generate AI slop with cats, which I did for this slide, and we want it fast. So, great example. And then we have data imports, very relevant to my own experience on the last project. Then we have also media processing and reports generation, and you name it, basically. So here I need to make a small side note. So you can notice that some of those jobs are I/O bound, some of them are not. But after yesterday's talk with Carmine, so thank you, Carmine, wherever you are. If you use an async job and fibers, it's going to be less of a problem because the latency going to decrease dramatically. However, it doesn't mean that the problem will go away. You're just kind of postponing it into the future. Plus, if you have like rate limits on your AI APIs, fairness will still matter because you're just going to shift the bottleneck from the worker CPU time to the rate limits. So whenever you have a limited resources, fairness matters. All right, so which one do we choose? And to be honest, we have like 4 approaches, and no size fits all. As always, it depends. Boring. So I would love to walk again through all of those, but I don't think I have time for that. Probably. So I'm just gonna say use the last one because in my experience, this is the only thing that worked for me on the last project, and we didn't experience any problems with scaling. And I tried everything, basically. So if it worked for me, I think it could work for you. And then, if you encounter problems, you can think of other approaches. So specifically for this talk, I implemented a gem that you can find by scanning this code. It's called Sidekick Fairplay. And it's mostly, OK, it's just for Sidekick, but it's like you can look at the source code, and it's not that difficult. You can adapt it to any background processor that you want. And yeah, and by scanning this QR code, you're going to find a lot more, because I have so much more to share with you, but I don't have time for that. So I put an extra document with more of my thoughts on those approaches, and the favorite blog posts and projects related to the topic. For example, about shuffle sharding, how shuffle sharding can be used to help with DDoS. The guys used it at AWS, for example. Or about interruptible iteration, like when should you use it and when should you parallelize. And of course, active job continuations, which are recently introduced in Rails 8. So at this point, it kind of just became the default good practice. And then we also have some amazing articles. One from my fellow Martian, Andrei Novikov, about throttling, and another one about leaky buckets. This is super fun. I love this article. I recommend reading it. And also some honorary Notion mentions to fuck you and farewell. Sorry, fareway. Okay. It didn't sound much better, but anyway. So the first one with the creative name, it's a kind of research project by our Vladimir Dementiev, where he kind of benchmarked these approaches. It's super fun. So check it out. And as for the fairway gem, well, again, scan the code, and you can read my thoughts on it in the document. OK, so as much as it would be epic to end the presentation at fuck you and farewell, alas, I'm going to end it with a positive note. I really hope that you learned something valuable today and that you worked up your appetite before the lunch break and that you never turn a customer away ever again. And also, for your sakes, I hope that the business owners of the restaurants nearby have been listening in to the strategies, because I think they're going to need it in about 10 minutes from now. Oh yeah, and one last thing. This is shameless self-plug. Please also come to the best conference, Ruby conference in the world, well, at least in SF. It's called SF Ruby. It's organized by Irina Nazarova, by the Titanic. Shouts out for Irina Nazarova, and also a lot of other people, like Amanda and Anton, and like a lot of people. Yeah. So yeah, and thank you all so much for listening, and bon appetit.